Hello and welcome to another episode of the Blockchain Interest Group podcast with your hosts Krishna and Nikhil. BIG is a consortium of individuals who are interested in blockchain and distributed ledger technologies. You can learn more about us on our website big-org.com or follow us on our social media using the links in the description down below. Our topic for today's podcast is IPFS, which stands for Inter Planetary File System. It is a peer-to-peer distributed file system that seeks to connect all computing devices with the same system of files. To understand IPFS, we need to understand a little bit about how files are accessed on the web. The internet uses the HTTP protocol to access and send data between computers. Typically, there is a client browser that connects to a web server over HTTP in order to exchange files. This system is usually centralized and therefore quite fast. The data availability is quite reliable, but it is censorship prone as well as easy to attack. IPFS aims to be a decentralized and censorship resistant file system for the web that aims to be equally fast and reliable as the existing centralized systems. Today, we are going to be looking at how IPFS works, how the network stores and transmits files, and its various advantages and disadvantages. With that, let's jump into our discussion on IPFS. So, Nikhil, do you want to start off with the basics of what IPFS is, how it is different from the existing web architecture that we know, and what is the problem that IPFS is looking to solve?
Sure. So basically, let's take IPFS. Let's take that question from the beginning. So we'll look at the problem that IPFS is trying to solve first. Then we look at the existing web architecture, and we'll get into what is IPFS. So the problem it is looking to solve essentially is the centralization of data, right? So right now, if you look at the web today, most of the files in on the web is served out of a few data centers. So you're talking about the cloud data centers, right? So majority of the traffic comes from AWS, Google, Azure, right? These are the main cloud providers, and then there's DigitalOcean and all the others.
Mm-hmm.
But again, if you look at the model of how the web interacts with each other, it is a one-to-one model, right? You're using the HTTP protocol, and you are actually you have a browser, and that basically goes to a web server. That web server basically returns it goes to the web server with a request, and the web server returns a response. And the request is basically a packet of data, and the response is usually in the form of a file, right? So this is the predominant mode in which files are being served. But the problem is HTTP is not meant for large files. Okay, so if you're taking about when you start thinking in terms of multiple terabytes of data, that's typically there in machine learning data sets, or large multiple gigabytes of data for high definition video and things like that. HTTP is not optimized for that kind of file transfer, right? So typically what happens is that you have other means, right? You go with other protocols, and you ask for that file in another way. But usually there is a HTTP link that takes you there, or an FTP link that takes you there. Now, what IPFS is trying to do over here is essentially try to take some of the learnings that have happened over the course of time. So peer-to-peer file systems, or rather peer-to-peer file distribution, is an old problem, right? It's been there from the beginning. We've always known that HTTP is not an ideal protocol for very large files. There have been various at trying to address that particular concern, right? So the attempts range from back in the day when we have FTP protocol to which is still like single client and a single server and susceptible to the problems of centralized systems. And then we came up. There was Napster, there was Kazaa, there was LimeWire, a bunch of P2P systems that came trying to kind of distribute the data amongst multiple nodes in a network to kind of reduce the load on a particular single server, and as well as distribute the storage amongst multiple nodes so that it's more reliable. They are still around, but they they all suffered from the challenges of being centralized, right? So they kind of you had a single point of failure and a single point to attack, and then when they were targeted, it stopped working. BitTorrent was one of the last ones of those. BitTorrent was relatively and continues to be relatively decentralized, but it still has a weakness in the sense that you still need an index or a particular listing or a search listing where torrent files or the links to the torrent files are made available, and that basically also leads to problems, right? So you target the link, and then there's no way of finding out what is there on people's machines.
Right.
So, so that's basically how existing web architectures work, right? You still predominantly go with HTTP for most of the file transfers. You kind of depend on Amazon and the big cloud providers to make sure that the files are being replicated and made available in multiple places and things like that. But they are essentially still a centralized location, and they all. So if Amazon goes down, large portions of the web go down, right? So how does IPFS want to replace this or change this? So what IPFS does essentially is, before we go into that, let's go into a little bit of a history. So IPFS was actually created, rather started by this person called Juan Benet. So he basically what he did was he looked at all the existing systems, distributed systems, and tried to look at how they handle files, and basically try to see if he could leverage the good points of these file systems together and create something that is more uh, reliable, better, faster, more secure, and and typically kind of more than just putting together a bunch of features, right? So
Right.
if you look at the original goal of Interplanetary File System, IPFS, the peer-to-peer file system that seeks to connect all computing devices to the same set of files. So one of the major differences between BitTorrent and IPFS is that IPFS could be considered to be like a single BitTorrent swarm, right? It's essentially one large file system that holds all the files in all its nodes, right? It's a global addressable what do you call it, space. So this is different from BitTorrent, where essentially you had every file basically becoming distributed amongst multiple nodes, and you create swarms where you have multiple copies of the same file, and then that. So it's all around this. The BitTorrent basically protocol is around a set of networks, essentially, each network being formed around a particular file, whereas IPFS tries to kind of create a overarching namespace where all the files have unique names and are available across the entire network. Okay, so so what are some of the key concepts behind the IPFS protocol, right? So basically, one basically looked at certain key papers and key concepts, and these include distributed hash tables. So this would be the distributed hash table is essentially the lookup table where you find out, who has copies of a particular piece of data, right? And there have been there are several implementations of DHTs. BitTorrent has one. There's one very popular one called Cademlia DHT. Then there is Coral DSHT, which is essentially a loose version of the Cademlia DHT, and then there is S Cademlia DHT, which basically addresses the security issue uh, where it uses a cryptographic puzzle for node ID creation that reduces chances of civil attacks. Right. So this distributed hash table is essentially the core concept. Another one core concept is the block exchange. Block exchange is basically taken from BitTorrent. So what BitTorrent uses is there is a data exchange protocol that kind of uses a tit for tat strategy, right? It rewards nodes who contribute to each other and punishes nodes who only leech from others. So essentially, if you look at BitTorrent, right, if you notice that you will notice that over time, if you are an active BitTorrent, if you keep your BitTorrent client on, right, and you keep sharing, uh, uh, uploading blocks as well as downloading blocks for your files, you find that your speed actually goes up over time,
Right.
right? So the reason why is because the protocol basically starts rewarding tit for tat strategies, right? So it also basically allows for the prioritization of pieces. So you can basically tell BitTorrent to send the rarest pieces first of a file. So that takes the load off of seeds. And so if you have the rarest pieces already on your local machine, then you don't need to have any seed that has the full copy of the file. You can just rely on peers that have the remaining portions. Right?
Right.
Mm. Then another very key system that one looked at is version control system, specifically Git, right? So Git basically has this idea of how to represent files in a system. There is the concept of a blob, where a file is considered to be a blob object. Then you have a tree of blobs, which is essentially a directory, and you have changes, which are essentially commits, right? So a version control system, basically, anytime you make a change to any particular portion of a particular tree, it actually creates a new commit object, right? And these objects are every time you create an object, the cryptographic hash of its contents are created. And basically, these objects are basically embedded into a they're linked to each other in a form of a directed acyclic graph, right? And this directed acyclic graph basically uses the Merkle tree principle. So where the hash object basically includes the previous, the child hash object, or the linked hash object, right? So the idea essentially being that at any point in time, it is easy to detect a change in that particular graph, and B, basically say, okay, if this particular parent hash, right, is matched, then that particular, all the children in that particular parent hash uh, are part of a particular file, right? So you can actually create very quickly, kind of uh, navigate this particular DAG, because it has the connections also in it, in the hash, right? Another because you have this Merkle DAG handling the low-level files itself, and it's a graph, right? Uh, you can actually have uh, instead of creating copies of a file, right? For any change that happens, you don't need to actually create a whole copy. You can actually, you can actually create an object that encapsulates just that particular change, and you can create a pointer to that particular object, right? So you can link to that particular object and say that, okay, this is the new version of this particular file, right? So it makes basically tracking changes to files very lightweight, and it also makes it very lightweight to create branches. So it creates, so if I say, okay, this particular directory set, right, there is one file somewhere that has changed, and I want to create a whole separate copy of it based on that particular file change, right? I want to treat them separately. You can actually create two pointers rather than keeping two copies of the uh, directory. So that kind of metadata based pointer references allows you to actually then very flexibly version things without much storage overhead, right? So that's one of the key features of Git that's again being used in IPFS. And then finally, but most importantly, there is actually it uses basically IPFS uses this global addressing system. So the files basically are globally addressable on the IPFS network, and it uses this concept from self-certified file systems. So SFS is basically the short form for that. They actually introduced a technique for addressing remote file systems using a particular scheme where they actually take, it's slash SFS slash, and then you put the location, which is the IP address of the server, put a colon, and the host ID. The host ID is essentially the unique ID, right? The host ID, sorry, not the unique ID. Host ID is a unique hash of the public key of that particular server and the location of that server. So the location being the server network address. So the advantage of this is basically now you have basically when you say, okay, I want to address a particular file or I want to access a particular file, and you give me a path like this. You say SFS hash location colon and then the host ID. I can immediately verify that this particular file system, right? The particular what do you call it, namespace, the particular URL that you've given me is actually valid, right? Because you can verify based on the public key offered, and not only that, I can immediately then send that public key to the server, negotiate a shared secret, and then secure all the traffic, right? So it's a self-contained kind of a thing. So the public key and the location combination basically allows for the for basically every file request to be done over a secure channel, because you require that for the participating server to have a public key and to make sure that every time it is addressed with this public key. Okay, and the other thing is the other advantage of that is all SFS instances share this global namespace, right? So since we are saying that the whole network is over under the same global namespace, how do you ensure that servers are not having the same name, or there are no collisions, right? And this basically allows you to do that, because what you're doing is essentially creating a cryptographic hash, and there's no coordination by any centralized body, right? It is inherently the key and location combination and the hash of that becomes unique. Okay. So these are the main concepts. So to go back, it's basically the Merkle DAG, distributed hash tables, block exchanges, version control, Git concepts, and self-certified file system, right? So these are the what do you call it? This is the history, or this is the legacy, or these are the giants on the shoulders of whom one is building the IPFS network.
Great. So I guess, with that, it's also worth just mentioning why IPFS is called Interplanetary File System. So, assuming that in the future humanity moved from Earth to several other planets, the client server architecture to store and access files as it is currently used would simply be too inefficient. So, for example, if information transfer from planet 1 to planet 2 takes several minutes or hours, even at light speed, each time a file request goes to a server on a faraway planet, it would take several minutes or hours to get even the smallest of files. So, in that case, an IPFS system of caching popular content on your own planet on distributed nodes would make a lot more sense. So, Nikhil, would you like to go a little bit deeper into how IPFS works and a little bit about the design of IPFS?
Sure. Okay. So we talked about how all these you know technologies that IPFS is kind of standing upon, right? So now let's get into, if you look at the design of IPFS, basically it actually stands on these kind of around 7 areas in which basically, or 7 things basically that it is designed around, right? Design features. Uh, just to emphasize, these are not like standalone things. They actually kind of come together to create IPFS, but it's useful to take them separately and discuss each one, right? So the first feature in the design basically is regarding identities, right? So how do you identify a node in a network, right? So the way nodes are identified in IPFS is using a cryptographic hash of a public key that is created using a static crypto puzzle. This is actually pulled from, or this is actually work that is borrowed from Escademlia DHT network idea. So the reason why you're using a static puzzle is to kind of discourage the creation of Sybil nodes, right? So it's make it expensive for you to actually create this particular ID, so you cannot just simply create a whole bunch of nodes. The nodes store their public and private keys, and they're encrypted using a passphrase usually. And users are free to instantiate a new node, but every time they launch an IPFS, they can instantiate a new node, but that actually loses any network benefits. So essentially, kind of like BitTorrent, right? IPFS is also rewarding or giving you uh, priority based on how long you've been connected and how much data sharing you're doing. So every time, but that depends on the fact that you have got a static. They can identify you, right? So if you keep creating a new node identity, then obviously that is lost. So nodes are incentivized to remain the same, right? Um, and again, regarding the hash function that is used, right? Another philosophy that IPFS adheres to is the idea of self-describing hash values. So here what is done is that the hash values are stored in a multi-hash format, which basically includes a header that describes the hash function and the length of the hash in bytes, along with the digest, right? So this actually allows basically that, okay, in future, if for whatever reason you need to change the hashing algorithm or the hashing method, it is basically easy to upgrade. You and basically be backwards compatible, right? Because the software can then see the header and figure out, okay, this is the algorithm that needs to be used, and then uh, compare that accordingly, right? So again, in terms of so these are the two main things regarding identity. So you have the self-describing hashing value, and you have these nodes. So the next big thing over here essentially is, so we can move on to the network feature or the network layer, right? So it's important to note that IPFS can use any network, right? It doesn't assume or rely on the fact that it has to be an IP system, internet protocol, right? It can be some other protocol. It can be any whatever protocol that you want it to be, right? it can be used as an overlay network also. So what is an overlay network? An overlay network essentially is that, okay, there is an underlying low level layer already, and you can actually build this as a logical network on top of that exists on top of that. So conceptually, you could basically have, say, something like, say, for example, a good example would be Amazon, right? Amazon might come and say, okay, take this IPFS thing, right? Internally, we will use IPFS to do the file management, right? And still expose an HTTP API to our clients, right?
Mhm.
It's, I mean, there's no real need to do that, but I mean, you could. And you could, in fact, do it the other way around also. You could basically have IPFS becoming a layer on top of Amazon S3. So suppose somebody has, say, some data they want to share between Amazon's cloud and Azure cloud and Google's cloud, and these clouds don't talk to each other, and they have this. So they can actually build a layer of, they can build IPFS as a layer on top of that, right? They can have nodes from Amazon, nodes from Azure, nodes from uh, Google, and nodes from whatever else, and they are basically all talking on top of whatever infrastructure has been built, right? So
Mhm.
this particular flexibility is there, right? And there is so the IPFS basically stores the address of a particular node or a particular location, right? We talked about locations earlier, right? The self-certified
Right.
file system locations. So there is so it actually stores it in what is known as the multi-address formatted byte string, right? So the multi-address format provides a way to express the address and the protocol that they are using. So, for example, if you're using SCTP and an IPv4 connection, so SCTP is secure transport protocol. IPv4 is Internet Protocol version 4, right? So you can basically have something like slash IPv4, you give your IPv4 address, and then you can put slash SCTP 1234. And it will basically be able to say that, oh, okay, fine, in you're using this particular, what do you call it, networking stack, right?
Hmm.
Now you can proxy that again. So suppose you want to do this over TCP, right? You can basically say, okay, IPv4 5678, TCP 578, IPv4 1234, and then SCTP 1234, right? So you can actually basically layer it as well. So it's a pretty flexible format and allows you to basically do this overlay. So the next piece in this puzzle essentially is routing, right? So all you have IPFS nodes, you have the network stack. Now you need a way for uh, one node to find another peer network address, and to find basically which peer can serve them the particular object that they require. Object being the file or the piece of data that they require, right? So IPFS uses a combination of the features of Escademlia and Coral. So it uses what is known as a DSHT. DSHT is a distributed secure hash table, and it basically uh, tries to take some of the features of Escademlia and some of the features of Coral to kind of improve performance of the DHT over previous versions, as well as keep it secure, right? So I talked about how we are using that cryptographic puzzle to prevent civil attacks. Uh, that comes from Escademlia, and that particular portion of it is also based on the Escademlia addressing system. So that it's kind of combining both, right? So your IPFS system is modular. Okay, so there is no if you find that you don't want to use this particular DSHT, you can actually replace it with another one of your own. Okay.
Mhm.
Now, data distribution in IPFS happens by exchanging blocks, right? So a block is then exchanged with the peer using the Bitswap protocol. Bitswap is something that came from BitTorrent, right?
Okay.
where what is actually happening is you have a set of blocks that you want, and you have another set of blocks that you have to offer in exchange. And so you go around to all the peers basically trying to see, okay, where can I barter, right? So it's essentially a barter, right?
Mm-hmm.
Now, one difference between BitTorrent and IPFS is, like I said earlier, IPFS is this global file system, right? So you're not restricted to blocks of a particular file or a particular torrent,
Right.
right? You can actually have swap any files, any block, right?
Mm.
So you can acquire blocks that they need regardless of what files blocks they have, right? The blocks could come from some unrelated files in the file systems. They just come together and know barter on that particular thing. So this makes it much more easier to kind of create, to find a particular path for bartering, right?
Mm-hmm.
So another challenge with this basically is uh, your this kind of works only on one level, right? So typically, what is the problem with the barter system? Problem with the barter system is if you don't have anything I want and I don't have anything you want, then we can't really talk to each other, or we don't really it doesn't really work. It needs to have complementary wants and haves, right?
Right.
So in that case, then what Bitswap actually tells the peer to do is that it basically says, okay, fine, go and find something, go and get pieces or get blocks that these other nodes want,
Mm-hmm.
and then basically go and exchange. So it becomes this multi-hop thing. It's kind of your typical barter problem, right? I have a shoe, I'm a shoemaker and I have a shoe and I want to buy some grain.
Right.
But the farmer doesn't need any shoes. So I have to go to maybe some, but the farmer wants, I don't know, he wants pesticides. So I have to go to the pesticide guy and see if he wants shoes. And he says, no, I don't want shoes, but I want manure. And then I go to the cow guy and he says, okay, fine, I'll give you manure based on the shoe. And then you kind of reconcile the whole chain, right?
Right.
So similar thing has to be done, right? And one advantage of that is that so one thing you have to do is essentially the protocol must incentivize nodes to seed, right? When they do not have anything in particular, because as they might have when they don't have when they don't want anything in particular,
Mm-hmm.
even though they don't want anything, they must be incentivized to provide blocks that others want. Because if there is like one block that only one node has, right, and it doesn't want anything, then the whole file transfer would get blocked just for the want of that particular block of data, right?
Right.
So how do you actually do that? So in Bitswap, nodes send blocks to their peers optimistically. They basically kind of act altruistically, right? In expecting that the debt would be repaid at some point, right? And this is where BitTorrent's problem starts, right? Basically, you have leeches where they will just keep taking the thing, they never return the favor. So, uh, what Bitswap uses, they actually track the balance. So they track the amount of data that is being transferred. So they basically say, okay, I've sent you so many blocks in terms of bytes, and the data basically. So when they send the block to the data, uh, the chance of you sending it again basically probabilistically decreases, right?
Mm-hmm.
uh, to function as as your debt increases to a particular peer, it will slowly stop, kind of throttle down the amount of blocks it will send you, unless you basically repay the debt, right? So this is kind of like what do you call it, uh, an incentive for peers to basically say, okay, fine, I can't just be keeping asking for stuff, because if I do that, then all the other guys basically, I'll have incurred a debt with all of these other peers, and then further down the line, I won't get anything from them because they would have deprioritized me, right?
Right.
So there's a whole bunch of what is that? Equations around that, and there's a ledger specification that allows peers to kind of keep track of what is being sent and what is being received. Right now, so this whole thing, right, this DHT and this Bitswap, this whole thing and this routing basically allows IPFS to create this huge, massive peer-to-peer system, right? On top of these, IPFS builds this Merkle DAG, right, which is a directed acyclic graphs where it links between objects like cryptographic hashes, right?
Mm-hmm.
Now, this essentially is how your what do you call it? Files are basically linked to each other. So how do you actually see? Because at the end of the day, if you look at blocks, right? Blocks are basically parts of a file. The data, as soon as a file is brought into IPFS, it is broken up into blocks and sent to different places, right?
Right.
So how do you kind of hold them together? So basically, what happens is there are two types. There is there are multiple types. There's actually the blob, which is essentially the file object, right? It's just nothing but binary. Whatever's inside it is inside it. It's content.
Mm-hmm.
Then there is the tree, which is essentially the object Merkle DAG, which basically it's not an object Merkle DAG. It's basically a tree. What the tree is basically is a set of is essentially a list of all the blobs that belong to a particular file.
Right.
Okay, that's another object. Then there is there's a tree for directories of objects. So sorry, directories of files. So essentially, obviously, you can have a group of files that are put together into a folder, right? So that particular folder or directory has to be characterized, and that's actually again characterized as a tree.
Mm-hmm.
Then you have a commit. A commit basically is any change that happens to a particular object. Okay,
Mm-hmm.
so the change itself is kind of put together as a separate object, and that particular is linked back to the original, right?
Mm-hmm.
So basically, when this happens, right? How do I put this? So this Merkle DAG basically comes together, and you can actually traverse this particular graph, right? So
Right.
you can traverse this graph using a string path API. They're like traditional Unix systems. The path basically is used and it makes it of the format, like, so you'll have path like hash IPFS, then the hash of the object, and slash then the name path to the object, right? So you can basically have IPFS, a huge hash number, and then slash foo.text,
Mm-hmm.
right? And if it's a kind of a directory, you can basically say IPFS hash of that particular tree, the tree of the directory, and then the path, so slash foo/bar, right?
Mm-hmm.
So and then obviously root is just a hash. So all of this basically now you have to store this somewhere, right?
Right.
So all IPFS clients have local storage, right?
Mm-hmm.
An external system where local raw data for the objects that IPFS is manages, right? This basically allows you to also basically pin objects to be kept in local storage. So one of the things is that ultimately, see, all the blocks available now IPFS are in some nodes local storage, right?
Right.
When users request the objects, you go and figure out which nodes have them, and then
Mhm.
pull it from that particular local object, and then put it into yours,
Right.
right? And so, so how do you actually? So sometimes basically you want certain objects to be made permanently available. It is usually a good idea for if you're like writing maybe you're trying to build a website on top of IPFS, right? And
Mhm.
you want the code in your website to be made readily available. So you can actually pin that to say that, okay, fine, this object is going to be kept in this node's local storage, right, all the time.
Mhm.
So it doesn't get swapped out during that particular bartering and all that, right?
Right.
The bartering and the swapping of the thing doesn't get this doesn't get affected. So
Mm.
every time anybody asks for it to be able to go and pull it locally.
Right.
Now we need to actually think about finally is the naming, right? So IPNS is the IPFS has a naming system, right? It's called IPNS, right? So the interplanetary naming namespace.
Mhm.
So so far we're basically saying that okay, we can actually create file paths using the Merkle DAG. We can actually traverse those file paths. We know that we can split your files into lists and blobs. Lists being the list of blobs that are there, files that are there, and then you have also got trees and what do you call it? Commits, right?
Right.
So this is all locally happening locally, right? In the UPF Unix file system. Now, how do I need to map this to a global IPFS URL, right? So to be able to basically say, okay, now slash IPFS slash hash num slash something is fine as long as it's local. How do I basically know which IPFS, how do I map this to a global system across multiple peers, right?
Right.
So that's where you need the naming IPNS naming system.
Mhm.
So, so in IPFS, basically the the Merkle DAG is an immutable Merkle DAG. Okay,
Okay.
so the objects that are created are permanent.
Mhm.
Okay, so every time you basically say, okay, I want this particular uh, piece of data, you upload a particular file, it breaks it up into a set of objects, creates cryptographic hashes and all that. Those are like one-time deals. Once they're done, once they've attached to that particular cryptographic hash, they are permanent. They are actually available on the IPNS at all times. So you can address them permanently from IPFS. The
Mhm.
next thing is that we're basically using the self-certified naming system that I talked about earlier,
Right.
right? So here, what we're doing out here is we're taking the IP address of the particular host. We are also taking the node ID, the ID of that particular file, and then basically taking it, putting it together as a location and host ID, and then basically hashing it together, right? So if you want, this basically maps to a DNS record. I'm calling it a DNS record, but it's actually uh, it's not DNS of the sense of uh, the domain name service of the internet. It is IPNS, the internet interplanetary naming system.
Mhm.
So this we what we are doing over here is we are basically using the self-certified thing to create a domain where it's a signed domain, right? And
Right.
then basically he created DNS text records. There is a lookup that allows you to basically say, okay, fine, this particular hash has a friendly name. Okay. So you can actually create what do you call it, friendly names for this particular location. The problem with hash is basically that it's not intelligible, right? It's too huge to remember. So you can actually, like in a DNS, you can actually map that to a particular friendly name. So like you can say ipfs.nikhil.io, right? And that is mapped to a particular hash address, hash of host ID and host ID and location. That basically allows the DNS record. So the node basically knows that this particular hash means that it has to go to that particular IP address, right? Now, so yeah, so that kind of overall covers the design of this particular uh, IPFS system. It's written in a language called Go, okay, and it's available open source. You can actually download this uh, right now. Today, you can go to, if you have a Mac or if you have, I mean, I think it's available in all the operating systems. You can download and run a node. I think it's a pretty straightforward process. They have executables and installables for every operating system, and you can participate in the IPFS network.
Great. So with that, Nikhil, can you tell us a little bit more about what are some of the problems that you might see with IPFS, or the kind of attacks that the network might be prone to?
Right. So IPFS basically, I think it does a good job in kind of taking some of the lessons from and the good features from earlier P2P network file sharing systems and kind of incorporating it. But then there are still some fundamental problems. See, at the end of the day, uh, IPFS is, there is a incentive problem, right? So IPFS, why would I want to run IPFS on my machine, right? There has to be some incentive for me, and that incentive usually is in the form of, okay, I want to be able to share some file, or I want to be able to receive some file, and basically that's the extent, right? I'm more interested in being able to maybe share a big file with my friends, and create this particular cache where I can actually dump all my huge files in a reliable manner, and I don't have to worry about my hard drive failing. Correct.
Right.
So the challenge with that is, okay, I want to do that, but at the same time, I have a bandwidth cost, I have upload cost, download cost. Why would I want to, if I can get away with not having to deal with that while at the same time leveraging the network, more power to me, right? There's a lot of incentive for me to try and game the system, but there's not much incentive for me to be a good actor, other than the fact that, okay, fine, they will uh, kind of reward me by making my files more easily accessible. Okay, so one of your classic attacks would be, okay, fine, I upload all these files um, from one place, then kind of shut down the node or whatever, and go and retrieve the files using another IP address and another node, right? So there is no, I can actually, like IPFS pointed out, it's you can actually regenerate your key essentially. So you can create a new node ID, and if you've done any bad behavior in the past, essentially it's wiped out, right? So you can start off with a clean slate. So that basically, there is a overhead in that. Okay, fine, you'll have to regenerate the key, but that is not a very significant overhead. You can do it once or twice, not a problem, right? Second thing is, okay, this actually gives a perverse incentive for popular files to be shared, and popular files will be more likely to be kept on the network over unpopular files. So, for example, in BitTorrent, right? If you take the old one of the main challenges with BitTorrent is that it is perceived as this uh, outlet or as this piracy kind of a thing, right? So you have every time you have a popular movie being released, the next day there is a camera rip-off or some kind of illegal copy of it made available on the torrent on the BitTorrent networks.
Right.
And but if you think about it, if you look at it, right, you would be able to get the latest movies for sure, no problem, easily. Probably the BitTorrent networks you'll get.
Mhm.
But if you ever go to a BitTorrent network and ask for something, from just 30 years old or 40 years old, uh, you're not going to get much. You may not
Right.
even get a single seed. And the reason why is because that's not something that everybody has interest in seeing right now. There'll be a very small population for that. It's going to
Right.
be the similar case with IPFS also, right? It's known as a tragedy of the commons. So it's a challenge where uh, you have all these you have this particular huge network, and most of the network is all these is basically copies of these popular files, and you want to upload your not so popular file, but there is no guarantee, or you can't really ensure that that is always going to be there with somebody. The IPFS global naming system ensures will say it says that okay, once you've uploaded it, it is there permanently. But again, at the end of the day, it's on somebody's local cache, right?
Right.
And if those somebodies, I mean, if there were only a few people who took that particular file in the first place, then there's a pretty significant chance that they may not be available on the network at the time you want, and the file may not be accessible even though it is the URL is there,
Right.
right? So that is one problem. Another problem we have is that okay, uh, it's very easy for people to kind of uh, create. I mean, this is a community effort, right? So
Mhm.
this at the end of the day, I'll put it on my laptop. I'll put it on maybe my Raspberry Pi. I'll put it on my home network.
Mhm.
There's no incentive for a commercial player to come and give you like world class. I wouldn't buy Amazon S3 space and kind of just to create a node in IPFS.
Right.
There's no commercial incentive. So
Mhm.
that's another main problem. So that means that the quality or the responsiveness or uh, the quality of service for your IPFS uh, network is very low,
Right.
and that actually then further dissent is a incentive for people to kind of participate,
Mhm.
right? So IPFS is great as a additional part of a larger network, right? So I would actually use IPFS in my DApp, or I might use IPFS for my for distributing my files. But uh, and then use it as part use it so that it's incorporated into my application, right? So the application backend, and then the value add is basically my application. So this basically means that IPFS has to be part of a larger system, right,
Mhm.
in order for it to be successful. And to a large extent, I think that's why, I mean, that's the reason why you're going down, why protocol labs and one basically went down the Filecoin path. Filecoin basically provides the economic mechanism, or the crypto economic, uh, how do you call it, the crypto economic system on which
Mhm.
basically Filecoin IPFS can be actually leveraged to become a reliable network and a reliable source of file storage, distributed storage network.
Right.
Okay, so that's basically both the problem and the solution for IPFS.
Makes sense.
Okay.
Yep. So, would you like to summarize, what you feel about IPFS? I know that it's been a long-standing technology, and it's going to become probably more relevant with an economic incentive that something like a Filecoin would bring on top of it. But overall, in terms of adoption and like how you see this technology performing, compared to the current architectures going forward, do you have any thoughts on that?
Yeah, I think from a technical perspective, IPFS is pretty solid. I mean, at least from whatever I have seen, I've actually downloaded a node and worked with it, and seems to be pretty straightforward.
Hmm.
Uh, as in all P2P network kind of solutions systems, the vulnerability is not in the technology so much as it is in the size of the network, right?
Hmm.
So IPFS is goal or stated goal to become an interplanetary file system for the entire internet and for the entire world. Uh, Obviously, is not we are in very early days right now. Having said that, um, I have noticed that IPFS is uh, becoming a tool of choice or a library of choice for a lot of decentralized applications or businesses, right? So I've seen Steam is using it for their video
Hmm.
solution. I've seen other D apps being created on top of IPFS. In fact, even in terms of developer tools, it's pretty friendly. It's a library that you can include. So I see that particular adoption driving IPFS forward, uh, and it's definitely growing. The one from one side, that particular growth is there. Um, on the other hand, I haven't actually seen, and perhaps maybe Filecoin would change that dynamic. I haven't actually seen anybody, the casual user, so to speak, use it that much,
Hmm.
right? I haven't seen anybody go and use IPFS to host their or put their images online, for example,
Right.
right, to replace Flickr or something. So
Hmm.
that again, I see is obviously a ways to go. I think Filecoin would be necessary for that. You need to have that kind of assurances that IPFS cannot give right now. So from a business perspective, I don't think IPFS was even ever meant as a business. It's open source. It's a protocol. They've built it as a library, and they've always talked about it as a library or an enabling technology. Right? When you say I want to become the file system of the world, that's not a business application. It's basically an enabling platform, right?
Correct.
And yeah, so the the I think from the perspective of perhaps what IPFS wanted to be, I think they are on their path. But how far along their path, how successful, I think there is a good chance that unless they solve that incentive problem, aligning incentives, have a problem, they wouldn't be an Amazon killer unless that happens, right?
Mhm.
And obviously there is also some unanswered questions about how fast you can retrieve files. Right now I think the size of the network might be a limiting factor, but I would be curious to see once they get to a certain respectable size whether their claims to be as fast as uh, existing systems is valid.
All right, folks, that concludes our podcast. We hope that you found this episode on IPFS useful. Please leave us your comments in the comment section below. Follow us on our social media. We are on Facebook, Twitter, LinkedIn, and also we have a very active Telegram group. The links for all are in the description below. Thanks again for joining. See you next time.